Thank you for that kind introduction. Today, I'd like to talk about bias in machine learning, and in particular in face recognition. See, face recognition is in kind of an unfortunate state these days where FR is known to do much worse on non-white faces than on white ones. In this story published in Nature in 2019, you can see that Native American faces are terribly inaccurately recognized by comparison to white faces, that black faces, again, very inaccurate compared to white faces, and even women, by comparison to men, are recognized poorly. The whole thing is kind of embarrassing, really. You can see this unfortunate woman trying to use a face recognition system to recognize features on her face, corners of the mouth, corners of the eyes, and so on, and was unable to get the system to do so until she covered her dark-skinned face with a white mask, where all of a sudden the system awoke and was able to see the characteristics of her face. And this unfortunate man, there was an article about him in the New York Times Magazine not long ago, was actually arrested because a face recognition system identified him as the culprit when in fact he was innocent. Now, unsurprisingly, given these sorts of stories and statistics, there's been a bit of a backlash against face recognition. In Europe, for example, there are articles all the time about concerns of the role of face recognition across European society. And the same is true on this side of the Atlantic in the United States, where we've been exploring what sort of regulations there should be around face recognition. To date, the Europeans have stopped short of blanket forbidding the use of face recognition, but it's a hotly debated topic. And in the United States, it's already the case that quite a few states of the Union already have legislation around personal information like face and iris being private information that cannot be shared and not be misused and so on. So this is kind of a hot issue, and rightfully so. In particular, this touches on the pervasive and really disquieting level of discrimination we see across our society, whether that's discrimination on the basis of gender or age, whether that's discrimination against Chinese folks or Hispanic ones, discrimination against anybody foreign, and the overall specter of racism. Now, nobody wants to hear a white guy talking about racism, but the point I'm going to make in this talk is that as disgraceful as racism and these other isms are, that's not the only reason that existing machine learning systems are manifesting this bias, where they do a much better job on white faces than black faces and Native American faces and so on. And in fact, even if we found ourselves in a world that didn't have racism in it, that didn't have all of these other isms and phobias in it, the strategies, the mathematical strategies we're using in today's inference engines would still have much of the same problem they currently have of manifesting bias in what kinds of things they recognize better than which other things. And that mathematical and statistical point is one I feel I can make, and that's what most of the rest of this talk is about, that there are things we can do to change our machine learning to reduce this bias, aside from the social ills around racism, et cetera. So to set a little context here, as you probably know, training a neural network minimizes a loss function. And the loss function that is almost always used is somehow reducing the average error on the different data points you're going to see. But now suppose that we had a face recognition training set that happens to have 10,000 white faces in it and only 100 black faces in it. What do you think a system that optimizes average error is going to do in that circumstance? Well, if the average error on a randomly selected white face is error sub W, and that on a black face is error sub B, well, the total error is going to be 10,000 times the average error on white faces, plus 100 times the error on black faces. In other words, the average error is going to penalize a certain amount of error on a white face 100 times as severely as it penalizes that same amount of error on a black face. That's right, 100x. Well, if we're going to tell our system, our optimizer, our machine learning system, that it's 100 times as expensive to make a mistake on a white face as it is on a black face, as in this circumstance, what do you think the system's going to do? It's going to make sure that it does a much better job on white faces and black faces, because that's exactly the measure, the loss function that we gave it to optimize. As we move our models more and more to the edge, this problem is even more severe, because in trying to compress our models, if we're going to do things like quantization and sparsification and the other techniques people use to make models small, well, you're trying to preserve as much accuracy as you can while throwing as much stuff overboard as you possibly can. If we've told the system that it's 100 times as expensive to make a mistake on a white face as on a black face, who do you think is going to get thrown overboard? That's right, the blackface. This is not a good situation at all, but is not caused just by racism, but also by these mathematical and statistical choices we're making in how we do our machine learning. So the canonical response to the argument I'm making is, oh, we just balance the data set. That is to say, if I have more white faces than I have black faces in my training set, well, I'll just add more black faces so I have the same number of both of them. And it sounds like that's going to fix this, but actually that strategy is naive, even if it's widely practiced. Because suppose I have more bearded black faces than I have clean-shaven black faces. What are you going to do then? Oh, okay, well, then I'll add more clean-shaven black faces. Okay, well, what happens if you have more bald bearded black faces than you have mutton chops bearded black faces? This infinite regress shows you're never going to fix this by balancing, because you can't have a representative number of each of the different characteristics that show up in every face. The guy with the mohawk and the eye patch, how many of those are you going to have, and so on. Just a digression for one slide for people who are more expert here in the audience. Another of the strategies one might use to try to address this are GANs, or generative adversarial networks. And for those of you who are less expert, a GAN is a type of neural network that generates synthetic data points that are visually very difficult to distinguish from real data points. So you can use a GAN to generate lots of new synthetic data to augment parts of your training set that might otherwise be missing. So you'd think you could use a GAN to fix this also, and add representative points that are missing in the training set. And in principle, you probably can. But if you look at how GANs are actually applied in practice, the only criterion people typically use is make sure each synthetic datum looks just like it came from the original data set. And if it turns out that generating a synthetic clean-shaven face that looks indistinguishable from a real one turns out to be easier to generate than a bearded face that's hard to distinguish, well, then again, we'll just generate more clean-shaven faces. If it turns out to be easier to generate a white face that fools the eye than a black face that fools the eye, well, it'll generate more white faces. So exactly the same problem of that imbalance I was showing earlier is preserved by GANs. And so that same bias that you had in your original data set with 100 times as many white faces as black faces can readily be preserved by a GAN, unless it's applied in a very careful way. Okay, so what should we do? How much influence should we allow each image to have so that the network doesn't suffer the bias that's being caused by this imbalance of features, imbalance of faces? Suppose that we have just one bearded mutton chop black man in the training set and have a zillion other faces, none of which looks like that. How do we make sure that this one guy can have enough votes that he is taken as seriously as every other kind of face that shows up in the data set, even though there's only that one representative? Well, in today's deep learning systems, every datum appears just once per epoch of training. You basically scan through the entire training set, ask what it thinks of the current model, and adjust the weights accordingly. And in a system that has average error, what we're going to do is take the error of each data point, divide by the number of data points n, and that gives us the average. Well, let's generalize that slightly and imagine that we can ascribe to each data point a mass. The mass is, if the mass is 1 for every data point, well, now we're back to average error. But we can take the weighted error, every error multiplied by its mass, and take the average of that. So now we can allow data points with high mass to have more votes than data points with low mass as a way of trying to fix that imbalance, to fix that bias. And we can still make the total mass be n, just as it was when we did average error. So we could now take our mutton chops guy and give him mass k, where k is greater than 1, and we can down mass all of the other data points as a way of making sure that the total mass is still n, but now Mr. Mutton Chops gets k votes. What's going to happen if you do that is that the gradient, when you're optimizing the weights of your network, is going to be k times as big for our mutton chops guy. And voila, I've now made Mr. Muttonchop's K times is important, right? And that's going to fix this, right? Well, unfortunately, not so fast. And here's why. Let's imagine that this is the surface of your loss function. So you're sitting here, and your objective is to get to the lowest valley in the entire space. And you do that in machine learning typically by computing the gradients. Basically, you compute the slope of the hill you're standing on, and then you move a certain distance specified by the learning rate in the downhill direction. And you do this over and over and over again until your sled takes you to the bottom of the valley. If we take some data points and say that they're K times as important, well, now we've effectively made the learning rate K times as big, but there's no particular reason to expect that someone who has a higher gradient has more runway to go downhill. You have a very local view when you're computing the gradient, and that longer sled ride might go uphill, downhill, or some combination of the two. So making the gradients bigger isn't likely to work well. What I'm going to suggest instead is that instead of making the mass of the gradient be K times as big, I'm going to select somebody with mass K times as often. That is, I'm going to have that same guy show up in K different mini batches, whereas guys who have lower mass will show up only once per epoch. So it can show up in at most one mini batch. So now our high mass individual gets multiple bites at the apple, gets to choose more than once per epoch which direction he wants to go in. And by taking multiple passes at him, his learning rate is the same at others, but he is able to move K times as far approximately per epoch. So that would work great if only I knew how to compute K. So I've now solved the problem of what would I do with a higher mass point to make sure I can optimize with it. How should I compute the mass? There are many papers by various famous people that would suggest that the importance of a data point is proportional to its loss. That is, every point should have loss 0 at the time you've optimized. So the loss in some ways measures distance from happiness, distance from having its constraints be satisfied. There are other points that say, no, it's not distance from happiness that's the important criterion. It's the gradient, the magnitude of the gradient that tells you how important the data point is. If I'm on a steeper slope, I have more to say about how the weights should change than you do if I'm on a steeper slope than you. And so gradient should be used for relative importance. I will argue that neither loss nor gradient is the right thing to do and propose a new idea instead in just a moment. So to give you intuition about why loss and gradient aren't going to do the trick, let's take points A and B, both of which have the same loss, but which have very different gradients. So A is going to move a little distance, whereas B is going to move a large distance because his gradient multiplied by his learning rate will move him much farther. So B is going to reach the finish line much sooner than A, and then the whole system is going to have to wait for A to catch up. So we shouldn't treat A and B as equals because they don't behave the same in the system. On the other hand, if we take two points C and D, that happen to have the same gradient, but have different loss values, well, now what's going to happen is that C moves a small distance, because it's based on the gradient. D moves the same small distance based on his gradient. C is much closer to the finish line than D is. And here again, we're going to have to wait forever after C has reached the finish line to wait for D to get to the finish line. So again, this is an inefficient strategy for deciding how much emphasis the system should put on each point while it's optimizing. As it happens, my mother was a junior high school math teacher, and many years ago, she taught me that distance equals rate times time, and thus time equals distance over rate. So what I'm going to suggest is that we have the time to happiness, that is, the magnitude of a point's loss divided by the rate. So it's distance to happiness divided by the rate at which it's trying to achieve happiness. And the idea is we want every data point to achieve happiness at about the same time. If you do anything other than this, that what's going to happen is either you're going to stop before every point has reached happiness, in which case you're going to have this bias that some points never got to the finish line. And when you see points that look like that in your test set, you won't fit them very well because you didn't let them finish optimization. Or you're going to wait for the rest of your life until all of the laggards end up finally making their way to the final optimum. So the only reasonable strategy here, I think, is to make every datum's mass be equal to its time to happiness. In other words, if a datum has more work to do, give it more time to get that work done. I believe that time to happiness is a better criterion for how much work to apply to each data point than either the magnitude of the loss or the magnitude of the gradient. This idea, which we call remassing, that is ascribing different mass to different data points, has the characteristic that it's optimizing worst case accuracy rather than average accuracy. By making more resistant data points get pushed for longer and seen more often, we're going to make sure that even the most difficult to optimize points make their way to happiness along with the easy to optimize points. And this is a good thing, that we're not optimizing the average anymore, but now worst case accuracy, making sure that nobody gets left behind, because essentially nobody cares about average accuracy anyway, even though that's what all the papers say you should do. I gave a talk on that exact point at last year's Embedded Vision, which you might take a look at. It's online if you're interested. But as it turns out, there's more you can do with remassing. It turns out that most data points aren't very interesting. Once you've seen a few faces of a given type, putting lots more in your training set isn't going to tell you very much versus much more unusual faces than that. So spending a lot of optimization time on data points that the model already fits is a waste of runtime. Remassing is telling you, spend your time where there's payoff, and then worst case accuracy will make sure that every type of data point is well optimized. So now we can finally get back to the point of this whole talk, which is about bias. By optimizing worst case accuracy and not average accuracy, remassing treats both the rare data points and the common data points as equally important. Every point, every feature gets the same loud voice. Now we're removing that bias that is a prisoner to how many of which kind of characteristics showed up in your training set, and are making sure every feature, everybody gets the same loud voice. So now if you have 10,000 white faces and 100 black faces, each of those faces, white, black, and otherwise, will end up getting a loud enough voice that they all get optimized, that they all get heard. And thus we have addressed a major source of the observed bias in face recognition. Now, I know that the organizers like us to have some extra resources you can look at. So here's a representative paper on each of gradient direction for mass and loss for mass, which I think should be subsumed by time to happiness, perceive my home base. And I'm also giving another talk at this Embedded Vision conference. Thanks very much for your attention.